This is a review of the answers for the Chapter 7 practice exercise. So the first question we have here is, what is the difference between a frequency distribution and a sampling distribution of the mean? Well, these are two very different things, and it's important to understand the difference between them, especially because your understanding of the sampling distribution of the mean is necessary for some of the higher statistical tests that we will be discussing. So a frequency distribution indicates the number of times that a variable takes on a certain value. So for example, let's say I wanted to know the average score that my students get on the first exam. So I take a sample of 60 students. Here's my 60 students here in column A. And a frequency distribution, again, will tell me how many students have scored a particular score. So here I have 2 students who scored less than 90. I have 5 students who scored from 91 to 105, 14 who scored from 106 to 120, 33 who scored 121 to 135, and 6 who scored 136 to 150. So again, I'm looking at the number of times that a student had scored a score of what is indicated in this column here. A sampling distribution of the mean, on the other hand, takes statistics of multiple samples. So for example, going along with this one, I could find the average score of this particular sample. And it comes out to be 123.8. I could take another sample of 60 students. They're still in the same population as Dr. C's students, but I could take another sample of 60 students and find that sample's average. I could take another sample of 60 of my students and find their average score. I could take another sample of 60 students and find the average of that class. Essentially, I can keep sampling, taking a sample of 60 students from the same population being my students, and creating a statistic, right? So these are statistics because these are calculated from a sample. And what a sampling distribution will do, it's creating a frequency distribution with these means here. So if I keep taking samples of 60 students over and over and over, I will create a distribution based on these means here. And I could hypothetically keep taking a bunch of samples, a sample of 60, and calculating their means. And from those means, create a frequency distribution. So that is actually our sampling distribution of the mean. We're actually looking at the means of a sample of 60, whereas a frequency distribution is just looking at one sample. A sampling distribution of the mean is looking at the statistic or the means of a bunch of samples. So as I am sampling, it's possible, but probably highly unlikely, that I could get a sample of 60 for only students who scored 85, right? What's the probability that I could randomly select a sample where all the students scored 85? Probably very little, but it is possible, statistically possible. I could, in the same sense, get a sample where everyone scores 100%. Again, if I'm taking a random sample, that's probably highly unlikely. But in the end, when I calculate these means, I would get a very low mean for this sample, and I would get a very high mean for this sample over here. And when you're looking at that sampling distribution of the mean, it turns out to be normal. Again, imagine if you are taking every possible sample that you could take from the population. Now, what you can do is take the mean of all of the means of all of the possible samples that you could take, and theoretically, if we take the means of all of these means, all the possible ones, an infinite number of samples, the mean of those means would be equal to the true population parameter. So that is the purpose of a sampling distribution. Okay, question number 2 is explain how sampling error is related to standard error. Why will you have larger standard error if you have a smaller sample size? So remember that sampling error is the degree to which samples will vary from one to the next, even though you're sampling from the same population. So even though all of these students are my students and I'm sampling from the same population, these samples vary from one sample to the next. We're not taking the whole population, so our samples will be different. Your standard error is the accuracy of that statistic. So if you remember back to chapter 1, we take sample statistics in order to draw conclusions about population parameters. And we want those statistics to be reliable. We want that statistic to be representative of the population parameter. If you take a small sample, say I have 1,000 students and I only take a sample of 5 students, how representative is that, or how likely is that going to be an accurate portrayal of the greater population? Not as likely as if I were to take a sample of 200 students out of 1,000 students. So having a smaller sample size increases your standard error because it's less likely that you're going to get a sample that's going to be representative of the true population parameter. And the last question is, why is the central limit theorem useful? So the central limit theorem says that if you take a large enough sample, the sampling distribution of the mean will be normal. So remember what a sampling distribution of the mean is. That's if you were to take all possible samples from a given population and calculate statistic, what would that distribution look like? Well, it would look normal, according to the central limit theorem. It's a little lumpy of a normal curve here. So for example, say I wanted to know the average weight of an American male. I can take a sample of, let's say, 100 men, and I'll calculate a statistic. I'll calculate the mean for these 100 men, and I find that the average weight for these 100 men is 180 pounds. Now, how do I know that my sample and my statistic is representative of the true population parameter? Well, according to the central limit theorem, again, that sampling distribution of the mean, if your sample size is large enough, will be normal. Like I had mentioned earlier, it is possible that we could take a sample and it's got a bunch of light weights in there and we get an average male weight of 100 pounds. Or we take another sample and we get a bunch of heavy weights in there and now the average weight of an American is 300 pounds. But what's the likelihood of that if our sampling distribution is normal? That's highly unlikely, right? But again, the sampling distribution of the mean of all those means is equal to the true population parameter. And we know from the empirical rule that 95% of the distribution will be within 2 standard deviations of the mean, right? So if this is a sampling distribution and I take one sample, one sample of 180 pounds, it's pretty likely that I'll be somewhere near that population parameter. So that's why that central limit theorem is useful. If you have a large enough sample, you can be fairly confident that your statistic that you calculate is somewhat close to the true population parameter.